In this lesson, we will learn some effects of refraction. We will learn some examples of everyday life where refraction takes place. The first example we will learn is a stick or a straw or a pencil partly immersed in water appears to be bent at the water surface. Like here we can see this is bent at the water surface. This also we can see it is bent at the water surface. Now we can explain this with the help of the phenomena of refraction. So here is a trough of water with a stick, maybe a pencil or a straw kept in water. Now why does this bending take place? When light emerges out of the water from this point, say here we have point A and this is the end point B. When the light emerges out, these are rays of light. I've just taken an example of two, and they will not travel in a straight line. This is not what's going to happen. They will bend at the intersurface because the refraction will take place. So since they are entering a rarer medium, they will reflect. And as they refract, here they will refract, and you're watching it now from, here's the eye. So these rays will now enter the eye. For us it will appear that these rays have come from, if we take it back, produce, it will appear the rays have come from this point. So now the pencil will appear to be in this position. So this will be the position of the rays, or the position of the pencil. The pencil will appear to be bent because here the refraction takes place. The bending of light takes place. Here's another diagram for you to understand. So the rays now are emerging from here and they're bending away. And if you produce these backwards, they appear to be at this point. So the pencil, which was earlier like this straight, no longer appears straight. It appears to be bent in this position. This is a clear diagram of why the pencil appears bent. So when light passes from water to air, it bends away from the normal due to refraction. Hence the stick appears bent at the water-air interface. Another example of refraction is an object under water appears raised. Like here we have a coin. This coin is just put in a beaker, but if you add water into that beaker, now the coin appears raised. It's actually at the bottom, but it appears raised up. Let's try to understand why this happens because of refraction. So here's a trough of water with the coin at the bottom. Now the light that emerges out from this coin at this interface, now it is entering into another medium from water to air. So here it will now bend away from the normal. And if you produce the rays backwards, they will meet at this point, and hence now the coin will appear to be at this point because the rays are meeting here. This is where the rays are meeting after bending. So the coin appears to be raised. Here's an example. So there is a brick at the bottom of the pond or the water surface of the water body, and the ray of light that comes out here, let's make it a little darker. At this point at the interface, it bends away. It does not follow the straight path. Here also it comes here. Now it is the interface. At this point it bends away. And if you now produce these rays backwards, so the rays appear to come from this position here. This is the virtual image of the brick. So the brick appears to be raised. This can be explained very nicely when for fishing in water. Now here is, you see a man who's trying to hit the fish. This is the real position of the fish. But when he's trying to hit the fish, he's not going to hit at this position. He's going to hit in a position a little lower. For him, the fish appears here. This is the apparent position of the fish. It appears to be here, but actually the fish is a little lower. So when he's trying to strike the fish, he's going to strike at a position that is lower than what he actually sees. Which means, if he sees a fish in this position, he's not going to strike here. He's going to strike a little lower, because the fish is actually a little lower. So again, the rays of light from the coin bend away from the normal at the water-air interface. Due to refraction, hence a coin or any other object in water appear raised. A pool of water appears to be less deep than it actually is. So let us explain this phenomena. So we take any point on the flow of the water, and the ray of light emerging from this point will now go a little bent. Here also, with emerging from here, it will not go in this direction. Instead, it will go bent because of refraction. So now the light appears to come from, if you back, it appears to come from this position here. So it will appear to us that the bottom of the water has been raised to this level. This will be the apparent position, apparent image of the flow. This is the real position, the actual position. We won't call it real, we'll call it the actual position of the flow. So the pool appears less deep than it actually is. The apparent height, depth of the water is this, but the actual depth of the water is much deeper. This is the actual depth of the water, but it appears much less. It appears just this much. This is again because of a refraction. We have seen the different effects of refraction. Just like reflection, refraction also obeys certain laws. At the interface of two different media, the light bends. But the bending of this light obeys certain laws. It goes according to a certain pattern. These are called the laws of refraction, which we are going to learn now. The first law states that the incident ray, here is your incident ray, then the refracted ray, this is the refracted ray, and the normal at the point of incidence, this is the normal at the point of incidence. All these three lie in the same plane. Incident ray, then we have the refracted ray, and normal at point of incidence, all these three, they lie in the same plane. This is the first law. The next law gives us a relationship between angle of incidence and angle of reflection. Now, what is the angle of incidence? Angle of incidence is the angle between the incident ray and the normal. So this angle is the angle of incidence. And the angle between the refracted ray here and the normal is the angle of refraction. The second law states The second law of refraction states that the ratio of sine of angle of incidence to the sine of angle of sine of angle of a refraction is a constant for a given pair of media and a given color. So which means it says that sine of angle of incidence over sine of angle of refraction is a constant, and this constant has been given a special name, and it is called the refractive index. So this ratio of sine of angle of the angle of incidence to the sine of angle of refraction is a constant for a given pair of media and a given color. And we give this ratio sine of I over sine of R. It's a constant, and we call it refractive index. So these are the two laws of refraction. We have seen that when light travels from a rare to a dense medium. Example of a rare would be from air, dense would be like glass. Then the speed increases. The speed decreases. From a denser medium, it decreases. And on the other hand, when light travels from dense medium to a rare medium, like from dense like glass to a rarer medium air, the speed increases. So during refraction, the speed of light changes. And now we will see a relationship between a refractive index and the speed of light. Here we have light traveling from medium 1, and then it enters into medium 2 and its speed changes. So this is medium 1, and in medium 1 the speed is say V1, and then when it goes to medium 2 the speed changes to V2. So the refractive index of 2 with respect to medium 1 is given as speed of light in medium 1 over speed of light in medium 2. To repeat, refractive index of 2 with respect to 1 is speed of light in medium 1 over speed of light in medium 2. That is refractive index of 2 with respect to 1. So let's write it again. Refractive index of 2 with respect to 1 equal to speed of light in 1 over speed of light in 2. Now what would happen if the speed of light was reversed? Now in this figure, the light is traveling from medium 2 to medium, this is medium 2, to medium 1. It will follow the same path. by reversibility of light. So here when we are measuring refractive index of 1 with respect to medium 2, and that would be speed in medium 2 over speed in medium 1. So refractive index of 1 with respect to 2 is speed in 2 over speed of light in 1. So in the first case, light traveled from medium 1 to medium 2, and hence we measured the refractive index of 2 with respect to 1. So we said refractive index of 2 with respect to 1 equal to speed in 1 over speed in 2. So that is V1 over V2 when the light traveled from 1 to 2. Now if we reverse the light, now if it travels from medium 2 to medium 1 in this direction, now the refractive index that we get will be medium 1 with respect to 2, and that would be, we know here this speed is V1 and this speed is V2. So this would be now speed in V2 over speed in V1. So if you observe very carefully, you find that refractive index of 2 with respect to 1 is equal to the reciprocal of refractive index 1 with respect to 2, because here we have V1 over V2 and here we have V2 over V1. In the first case, the light traveled from medium 1 to medium 2. So we measure the refractive index of 2 with respect to 1. And in the second case, light travel from medium 2 to medium 1. And then we measure the refractive index of 1 with respect to 2. So here we measured 1 with respect to 2. And in this case, we measured 2 with respect to 1. And they were reciprocals of one another. Which means if light travels from water to glass, here is speed in water V1, speed in glass V2. So here we would have got refractive index of glass with respect to water, and that would be speed in glass, which is V2. That would be speed not in glass, speed in water, because it is coming from water, over speed in glass. That is V1 over V2. But if the reverse happened, if light traveled from glass to water, then we would get the refractive index of water with respect to glass, and that would be speed in glass over speed in water. So refractive index of water with respect to glass would be then V2 over V1. And if you observe this carefully, the refractive index of glass with respect to water will be equal to 1 over refractive index of water with respect to glass, reciprocal of one another. We'll now learn what is absolute refractive index. Now if this medium 1 is A, then the refractive index of medium 2 is said to be absolute refractive index. which means if light is traveling from air to another medium, what we measure is called absolute refractive index. Example, if light is traveling from air to glass, the refractive index measured here is called absolute refractive index, because we are going to measure refractive index of glass with respect to air, and that will be speed in air over speed in glass. This is called absolute refractive index. So if medium 1 is vacuum or air, then the refractive index of medium 2 is considered as absolute refractive index. So absolute refractive index is speed of light in air over speed of light in medium. This is absolute refractive index. Let's take up an example. For example, we want to find absolute refractive index of water. It means speed in air over speed in water. And when the light travels, it would travel from air to water. Speed in air, say this is V1 and this would be your V2, and what you measure now will be absolute refractive index of water. Another example, suppose we want absolute refractive index of glass. That would be speed of light in air over speed of light in glass. So in general, to repeat, absolute refractive index of any medium is speed of light in air over speed of light in medium.